An airplane flies 280 kilometers on a bearing of 9 degrees from Calgary, Alberta, in Canada to the provincial capital, Edmonton. From Edmonton, a plane flies 1,320 kilometers on a bearing of 72 degrees to Churchill, Manitoba, located on the shores of Hudson Bay. It says, how far is Churchill from Calgary? So first we need to draw a diagram. I'm going to draw it on a separate piece of paper because I think sometimes with bearing problems, it's nice to just have space. So we start at Calgary from a bearing of 9 degrees. So I'm going to start here with my little north, south, east, west. 9 degrees is a really small bearing. So I'm going to exaggerate it a little bit just so it's easier for me to see. And again, that starts from Calgary. So I'll label that as Calgary. And a bearing of 9 degrees means that this guy is 9 degrees. Remember, we peel off from north, right? So that's a 9 degree. Then we change our bearing, which means this is where we are, and we change the direction we're going. So we build another north, south, east, west. And from there, we change our bearing to 72 degrees. And that's from Edmonton. So this is Edmonton. And we go to 72 degrees. So from here, a peel off of 72 degrees would be like that. And that angle right there is 72 degrees. We also have distances that we're going. So the airplane flies 280 kilometers on this bearing, which means with this bearing, I go 280 kilometers. So that length is 280 kilometers. Then my second bearing, which is 72 degrees, is 1,320 kilometers. This is your more applications level IB material. So it's going to be tough, and also we can get through it. We're using all the skills that we had before, and now we're just applying it in a tough way. It then says, here's Churchill. How far is Churchill from Calgary? How far are these 2 points? Well, in order to know the distance between 2 points, it's the line or the segment really that connects those 2 points. So I have to draw in a line or a segment that represents that distance. And that is the distance I want to solve for. So how do we solve for that? Well, we can see that we have a triangle, and sometimes taking it out of the bearing situation and just redrawing it as just a normal triangle can kind of help us see what we have and what we don't have. So I'm going to kind of redraw the general idea and fill in what I have. I've got 280 and I've got 1,320, and I want to solve for this guy. And it's a non-right triangle, so we're going to use either law of sines or law of cosines. And I know with all of these, I need to have an angle because we know side is not a way to prove that two triangles are equal, which means there's no way to have one unique triangle in this situation. There's a bunch of different triangles that we could use in this situation. So now I need to go in and say, how are my bearing problems going to help me? I know that I don't know this, but I'll tell you, this is going to be the angle that we can solve for. I can't really solve for this angle right here because I don't know any other information besides this being 9, right? This could be anything depending on where this line is coming from, right? Because I don't have this angle locked in. So this could be over here or it could be over here. So I don't have enough information to solve for this angle. I don't have any information to solve for that angle. So I've got enough information over here. I could probably solve for a few things. Again, with problem solving, we don't normally know where we're going to end. We just need to try something. So start seeing if you can find relationships. Label any angle you can think of, even if it's 90 degrees. Okay, that's 90 degrees. Awesome. Start labeling and figuring out and puzzling what you can and cannot figure out. Something that you can figure out, hopefully, is this angle right here. If you know that this angle is 72 degrees, what must this angle from here to here, what must that angle be? Since from north to south we have 180 degrees, all I have to do is subtract out 72 from 180. And that gives me 108 degrees. Now realize that that's only a part of that angle, right? It's only this part of the angle that's 108. I still have this whole section of this angle that I haven't solved for. And this is where remembering that that north-south is always parallel is going to be key. Since this is 9 degrees, these guys are, since this is north-south, this other north-south is parallel. And this guy is our transversal. This angle and this angle are actually equal because of parallel line transversal relationships. Alternate interior angles. The main idea with parallel line and transversal relationships is all small angles are equal to each other and all big angles are equal to each other. And as long as you can remember that, then you can remember, oh, that and that must be equal. So that is 9 degrees, which means if I wanted to know this whole angle, all I have to do is add 108 to 9, and I get 117. So this angle in here, just double checking that that's correct, yes, is 117 degrees. That's a lot of work to get to this, which then we can use either law of sines or law of cosines in order to solve for x. The tricky part here is the multiple bearings. So doing now multiple north, south, east, west lines, and then being able to solve for angle measures. If you ever need to grab an extra piece of paper to have all the space that you need, that is always something you can do, even on a test. I would try to recommend drawing, if you did this on a separate piece of paper, drawing it in here in some way, shape, or form. But I just wanted to make sure that you could see what angle I was talking about as I was making that. But here's the general idea of the triangle we have: 280, 1320, 117, and x. When to use law of sines and when to use law of cosines. The main thing I'm going to tell you with that is just try something. Try law of sines. If I did law of sines here, it would be sine of 117 over x. And then, okay, I don't know that angle, so I'll label it theta equals sine of theta over 280. Oh, I've got a variable and a variable. So I can't solve for that because there's too many variables. I want to only have one variable. So if I set up a relationship and it has too many variables, I use the wrong law. So instead of just memorizing when I should use something and when I should use the other thing, just try it. And if it's wrong, you're like, oh, okay, I hit a dead end in this maze. I'm going to backtrack and try a different path. I hit a dead end with the law of sines. So what if I do the law of cosines? Well, that would be x squared equals 280 squared plus 1,320 squared minus 2 times cosine of 117. And now I can see, okay, I only have one input, which is x. I only have one variable. And so now I can solve for x because that's pretty straightforward. Again, x squared is equal to 2156389777741, yada, yada, yada. I'm going to take the square root and I get 1468.47, which if I wanted to write this in 3 sig figs, that would be my third significant figure. 8 is telling me to round up, so I would answer it as 1,470 kilometers. And that's how far Churchill is from Calgary. But we had to find first all of this bearing stuff, which looks pretty cool when you see it at the end, but is stressful in the middle. We will practice this in class for sure. If an airplane flies at an average speed of 720, how long is a direct flight from Calgary to Churchill? As you saw in our previous test, knowing the relationship between speed, distance, and time is just a must in this class. I don't know if some of you are taking, I don't know if it's in physics that you learned this, but in one of your science classes, I think you learned this triangle that's speed, distance, time, where like distance is equal to speed times time. If I wanted to find time, it's distance over speed. It's this like triangle of fractions or multiplication. I didn't learn to think of it in that way, so how I think of it is slightly different. I always base off of how I measure speed. And how I measure speed in my brain is miles per hour. But maybe you measure speed in kilometers per hour. But I think, oh, kilometers, distance, hour, time. So speed is always equal to distance over time. So then if I wanted to find out time, I would just need to isolate for time. And I know, okay, well then time would go over here, multiplied by speed equals distance. Okay, so time is equal to distance over speed, which you can see that in this triangle. Time would be distance over speed. And that's why that triangle is helpful, but this is how my brain works with it. So if I wanted to find time, I need the distance over the speed, and the distance that I travel from Calgary to Churchill is this guy right here. I'm going to use my exact value and not my rounded value because I am a smart math student and I know the importance of being specific. So I'm going to use the exact value, 1468.47, yada, yada, yada. Divide it by the speed, which is 720, which gets me approximately what? We get approximately to 3 sig figs, 2.04, but it does tell us to the nearest hour, so I would have also accepted 2 hours as your answer. Okay. The hardest part about this lesson is figuring out bearing, and that's going to be really, truly the IB level problems that we're going to be using law of sines and law of cosines. Also, three-dimensional geometry uses law of sines and law of cosines quite a bit. Well, actually, we use it a lot. So we'll see a lot in class of all the different ways that it will be applied, and we will practice that for sure. Good job today.